Hey you guys, in this statistics video I want to take a look at what we would call a binomial distribution. Now, I'm finding probabilities of a binomial random variable might be another way for us to describe this. So what I want to do to start this video off is look at a relatively simple example just so we can get our hands dirty with what this process looks like, where we can see actual numbers and make sense of this, and then we're going to abstract to a more general formula. All right, so in this example, right, let's suppose that suppose we are taking a multiple choice test with 3 questions. Not a very realistic type of multiple choice test, right? But just go with me so the numbers are manageable here. So we're taking a multiple choice test with 3 questions, and each question has 4 answer choices, right? Each question has 4 answer choices. So let's say an A, B, C, or D, 4 possible answers we could pick from. Now, what I want to assume here, and this is a little crazy, right? But let's suppose we walk into a class, and on the very first day, our teacher gives us a pre-test, right? Teacher wants to see what we know about the content. Now, let's assume this test is super duper hard, and we have no clue what any of these questions are asking. So on each of the questions, we are purely randomly guessing. We have no clue. We can't eliminate an answer. We have no idea what these things are, and we're purely guessing randomly. So let's suppose that, right, we want to determine what's the probability we get 2 out of 3 correct. Right? So let's say, what is the probability we guess? What's the probability we guess 2 correctly? Okay, so in order to attack this problem, what I first want to do is consider all possible outcomes in our sample space. So back in a prior video, we talked about using a tree diagram to list all possible outcomes of a probability experiment. So the way I'm going to structure my tree diagram in this scenario is I'm going to do it in kind of a vertical manner. So let's suppose I'm looking at question 1, and then question 2, and then question 3. So what I'm going to do is list each possible outcome for each of these scenarios. So with question 1, I could either answer correctly or not. So I could have a success or a failure in answering correctly. Now, here's why we call this a binomial random variable or binomial probability, right? We either have a success or a failure. We have 2 possible outcomes, and that's where, bi comes into binomial. Right? So we have 2 possible outcomes in every binomial experiment, a success or a failure. So for this particular situation, right, we have the first question being multiple choice, and I'm randomly guessing I'm either successful or I'm not. So if I answer the first one successful, question 2, I could still answer success or not. And then if I answer the first one as a failure, I could answer the second one successfully or not. And then repeat. So if I answer the first one successful, then the second one successful, then for my third question, I could have success or failure, and then I could have success or failure here. I could have success or failure here, and success or failure here. So again, this was what we called a tree diagram, and it allowed us to visualize all the possible outcomes. So if this is how I could successfully answer each question, let's look at all the possible outcomes. So remember, the beauty of the tree diagram is I can just connect all of these branches together. So if I look at this first branch, let me move backwards. So if I answered successfully on the third, successfully on the second, and successfully on the third, I'm technically going to go in the other direction. So question 1 was success, question 2 was success, question 3 was success, and there's 3 successes in a row. Now I'm going to come off of this branch, right? I'm going to go backwards here. So I have success, success, and then failure. And then if I come off of this branch, right, I'm going to move backwards along that branch. Success, failure, then success. And I'm going to continue through each of those paths. Success, failure, failure. And then I have coming off this branch, right, I'm going to move backwards, failure, success, success. And then I'm going to have failure, success, failure. Then I'm going to have failure, failure, success. Then I'm going to have failure, failure, failure. All right, so there's 8 possible outcomes in our sample space, and that should make sense, right? We had what we called the counting principle, where we talked about if we had 3 questions, we had question 1, question 2, question 3, have 2 possible outcomes for question 1, success or failure, 2 possible outcomes for question 2, success or failure, 2 possible outcomes for question 3. The counting principle says 2 times 2 times 2 is 8 possible outcomes. And that's what we can see in what we listed over here in our tree diagram. Now this question is asking for what's the probability of 2 successes out of 3 trials. So first of all, let me switch to gray here, and we'll notice that here we have 2 successes, and here we have 2 successes, and here we have 2 successes. So one thing to keep in mind that we see visually in that tree diagram is the ordering and the successes doesn't matter. So whether we get the first 2 questions correct, or the first and the last question correct, or the last 2 correct, either of those 3 situations, we have gotten exactly 2 questions correct and answered 1 incorrectly. All right, now if we keep in mind back in our probability chapter, one of the things we talked about was if we were finding the probability of a successive number of events, in this case 3 events, answering each question, what we would do is find the probability of each scenario. So if I look at this one first, right, let's list out the probabilities of each of these. Probability of each of these situations. So if I look at this one first, the probability of success is out of the 4 answer choices, A, B, C, or D, there's only one of them that's correct. So I have a 1/4 chance, right, or 25% chance of getting the first one correct. Getting the second one correct, I would have a 1/4 chance. And getting the third one wrong would be 3 out of 4 are incorrect. So if I multiply all of those, I get 3 divided by 4 cubed, which is 64. All right, so technically, this one's going to be the same answer. Have success for the first one, which would be 1/4. I have a failure for the second one, which would be 3/4. And then I have a success for the last one, which would be 1 out of 4. And I'm going to get the same probability there as well. And then ditto for this guy. I mean, technically, this one is 3/4 times 1/4 times 1/4, which is going to give me 3 out of 64 in that situation. Now, I could do these other ones, and I'll do a couple, but I don't want to do them all just for the essence of time. Success, success, success would be 1 out of 1/4, 1 out of 1/4, and 1 out of 1/4. And that would give me 1 out of 64 in that case, right? And then let's say this guy, failure, failure, failure. So I have 3 out of 4 which are wrong. Right? I have 3 out of 4 which are wrong, and 3 out of 4 which are wrong, and I'd have 27 over 64 in that case. So we could complete all of these in that same manner. Now, what I really want to do is add all of these together that meet my question that I'm asking. So the question I'm asking is we get 2 questions correct out of the 3. So again, we have 3 of those that occur. So I have 3 out of 64 plus 3 out of 64 plus 3 out of 64. And a shorthand way of writing that is to just say 3 times 3 out of 64. Right, so let me switch back to blue. So the probability that I answer 2 correctly, I get 3 successfully correct, is 3 out of 64 plus 3 out of, ooh, that's not correct, is that right? Yeah. 3 out of 64, 3 out of 64 plus 3 out of 64. So I really have 3 of the probabilities in that case. And let's go ahead then and convert that to a decimal real quick. That would be 0.1406 if I round to 4 decimal places. Okay, so in examples, or I should say problems where we have a much larger number of trials, if you will, right? In this case, we had 3 trials. We answered 3 questions. What if we were answering, 50 questions, and I want to find how many could I get, 4 of them successful? That's a humongous tree diagram, and that's not something that I really want to do. I don't want to go through that process. So what we want to develop here is a shortcut. So we're going to look at a formula which would count this for us in essence. And what I want to do is look at this smaller example to just make sense of where this formula comes from. So I just wanted to scroll back up real quick, and if we look at each of the probabilities that satisfy our event, right? So our event was getting 2 successes out of 3 trials. And if we look at each of these, right, notice that I have 2 successes, so I have a quarter times a quarter. Here I have a quarter times a quarter, and I have the same thing down here, quarter times a quarter. So keep in mind, algebraically, when you multiply something to itself twice, you have an exponent of 2. Right? So in other words, I'm going to scribble up here and then I'm going to rewrite it at the bottom. If I have something times itself twice, that's x squared. So what we really have in this particular example is a quarter times a quarter, or a quarter squared. And I want to also point out to you, for this particular example, that is the number of successes that I have. And so that is going to be the generalization. What we're always going to look at is the probability of success, which is a quarter. Our probability of success in this case is a quarter, and then the exponent on that success is how many successes that we wanted, right? We wanted 2 successes in this scenario, so there's our exponent. So we really have 1/4 to the power of 2. And then lastly, we have a failure. So we have the probability of the failure, 3/4, and then the exponent is how many failures we have, right? In this case, we have 1 failure out of the 3 trials. So let me write this down as a formula here, and then we'll discuss a little bit more deeper, right? So in this situation, right, what we were looking at is we had the probability of success. And in fact, let me come back over here for a second. We had a probability of success of a quarter, and we had 2 of those. We had 2 successes out of 3 questions. And then we had a probability of failure that was 3/4, and there was only 1 of those. Now, we could write this a little bit of a different way, and I'm going to leave a little bit of a gap in the front because I want to look at this number in the front. Remember, the number we have here was 3. Right, so I want to look at that number in the front in this case. So first of all, I have 3 total trials, right? 3 questions that I'm answering. So another way that we can write this is we could have 1/4. We could have the success probability raised to the number of successes we want. And then how many failures am I going to have? Well, technically it's going to be all the possible trials minus the number of successes. So in this case, we had 3 questions. We got 2 correct. How many are left over to be incorrect? Well, the 3 total minus the 2 correct gives us the 1 left over to be incorrect. All right? So when we see our formula, that's what we're going to see. We're going to see the probability of getting something correct to the power of how many successes we're looking for. And in this case, that was 2 successes. Then we're going to look at the probability of getting it incorrect, or a failure. And then how many failures would we have? Well, out of 3 total questions, 3 minus the successes gives me the number of failures left. All right, now let's look at this number in the front. So in this situation, what we were really counting here is how many had 2 successes. So out of the 8 total outcomes that we listed above, how many had 2 successes? So again, let me scroll back up. So in this case, we were looking for answering 3 questions. So when we answer 3 questions, we get failure times success times failure or success times failure or success. We have 8 possible outcomes. That's what we have in our outcome list. And how many had 2 successes? That's what we were asking for. We had 1, 2, and 3. So that's what our coefficient is, if you will, of my probability, right? So this coefficient right here is how many ways are there in this case, of getting 3 successes, right? So for us, this was 3, and then I didn't really give myself enough room here, right? This number is how many ways, right, to get, we had 2 successes, right, out of 3 trials, the 3 questions we answered. So for this particular problem, those are the ways we connect those numbers together. Now, anytime you look in a statistics textbook, they're going to use a particular version of a formula to describe what we're looking at. Right? Now, for this specific example, here's how we would be plugging into the formula. This first number here, we call the binomial coefficient. We're going to use the letter C. And in this case, the letter C, we'll discuss that more in a second, we had 3 total trials. We wanted 2 successes. All right? So this binomial coefficient with 3 total trials, choosing 2 successes, that would turn out to be the number 3. Well, again, I'll come back and show why that's the case in a minute. Right? But this is the shorthand notation we use in our formula. Then we multiply that number times the probability of success. So in this case, we had 0.25 as our probability of success, and we wanted 2 successes. And then we had our probability of failure, if you will, and that was 3 minus 2. So the relationship that we have in this formula, we have 3 trials, 2 successes. We have the probability of success to the power of the number of successes. And then the number of trials minus the number of successes is how many failures we have. So the probability of a failure to that exponent. Now, again, when we look in a textbook, what we typically see is the following formula. We typically see something like this. Out of n trials, the binomial probability of, we're going to say, x successes is given by this formula. So the probability of x success is given by, so if we have n trials, we're choosing x successes. That's going to be the probability of the success to the number of successes we want times the probability of failure to the number of failures that we have left over. So this would be the formula of a probability of a binomial random variable, where we have n trials, we're looking for x successes. We know the probability of a singular success, and we know the probability of a singular failure. So again, anytime you look in a textbook, right, this is the formula we write, and n is the number of trials. So for our example, that was answering 3 questions. Right? X is the number of successes we are interested in. And then P is the probability of a success. Oh, that's not a T. My hands don't want to follow my mouth when I say here. So the probability of a single success. What was the probability of getting one of the questions correct? 1/4. And then Q is always 1 minus P, right? This is the probability of a failure. Probability of a failure. And, you know, like we talked about in the prior video on probability, that's the complement rule, right? So Q equals 1 minus P. So again, in this particular example that we had, right, for our particular example that we had, we were answering 3 questions. We wanted 2 successes. Let me write X. We were looking for the probability of 2 successes. We knew the probability of 1 question being successful was the 1 correct answer out of the 4 answer choices. And then the probability of failure would be the 3 out of the 4. So if we plugged into our formula, right, the probability that X equaled 2 successes for our formula, we had the 3 trials, choosing 2 to be successful. we had our probability of success, and we had 2 of those, and then we had the probability of the failures, and we would have 1 of those. Right? Now, we do have technology that can help us crunch these numbers, and I want to talk about that in just a moment. Right? But if I'm doing this by hand, right, how do I find that binomial coefficient? So how do I find this number? Now, in our example, this was 3. There were 3 ways of us getting 2 successes out of 3 trials. Now, back in a prior video on probability, you talk about 2 different types of counting techniques. One counting technique being a permutation, one counting technique being a combination, which is what we're using here, a combination. Now, back in that type of discussion, you would say a permutation is counting the number of ways something occurs, where ordering matters. So having our 2 successes first and our 2 successes last would be counted separately. So a binomial coefficient, what we would call a combination, an accounting conversation, would be the ordering doesn't matter, which is what we saw in this example. The 2 successes could come first, could be first and last, or it could be the last 2 questions we answered successfully. So the ordering doesn't matter. So back in a conversation on counting techniques, if we have what we call n choose x number that we're counting, so n possible trials, x successes, if you will, right? What that's going to be is n factorial over x factorial times n minus x factorial. So in this particular case, we would have 3 choose 2. So that would be 3 factorial over 2 factorial times 3 minus 2 factorial. Okay. Now, I don't want to go in gory detail here because this is something we've already discussed. But in this case, a factorial, remember, let me come back over here. So I'm going to bring this number down here. Factorial is that number times all possible natural numbers, right, down to 1. So 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. And this is 1 factorial, which is just 1. You know, so if I had in the numerator 7 factorial, that would be 7 times 6 times 5 times 4 times 3 times 2 times 1. So in this case, if I multiply all of this out, I get 3 times 2 times 1, which is 6. I get 2 times 1 times 1, which is 2. And there was the 3 ways that we got our 2 successes out of 3 trials. So this is a binomial coefficient. It's a number of ways of finding x successes out of n trials. All right, now let's talk about if we were using technology to do something like this. So let's suppose that we're using a Texas Instruments, a TI calculator. Right? So I'm going to go ahead and pull up a TI calculator here. And on my TI calculator, what I'm going to do is I want to find the binomial distribution. So you will notice above the vars key, I have distribution in blue. So I'm going to do second vars and go to the distributions. And I can see a whole list of distributions here. And if I just start to scroll down, we're going to find the binomial distribution right here. Now there's 2 binomial distributions. One is called the PDF, the binomial probability distribution function, and the other one is the binomial cumulative distribution function, right? And cumulative we'll talk about in just a moment, but in this case we're doing just the PDF. We're finding the probability of exactly 2 successes. So if I choose binomial PDF, it's going to bring me to the home screen and it's going to ask me for that information that we wrote down. So for example, we had 3 trials, we had 2 successes. Our probability of success was 0.25. So once the 3 trials that we had, the probability of success was 0.25, and then I want 2 successes out of this problem. So if I click paste, it brings me back to the home screen and plugs these numbers into the pre-written program that somebody at TI wrote for me. That was very nice of them. And I'm going to hit enter again. And there's the decimal value of what we got from our problem. So we can see, if I minimize the calculator here, right here was the decimal value that we got for the 2 successes out of 3 questions. Now, let's suppose that we're using Excel as our calculator. So if I bring up Excel real quick, What I'm going to do is use the binomial distribution that's built into Excel. Let me see if I can minimize this just a hair so you can see this. Right. So what I'm going to do is select any cell. I can select any cell here. I'm going to come up to the formula bar, click, and I'm going to hit the equals key, and I'm just going to start to type binomial. So as I start to type binomial, you can see that it's populating. It's guessing what I want. And what I want is actually the very bottom one, binomial distribution. So I'm going to choose that. Double click, and it's telling me what it wants. So it wants the number of successes and then a comma, and then the number of trials and then a comma, the probability of a success, and then is this cumulative, which in this case it is not. We have exactly 2 successes. So for us the number of successes was 2, so I'm going to type 2 and comma. The number of trials that we had was the 3 questions we were answering. The probability of a singular success was 0.25, and then was this cumulative? I'm going to say false. Close the parenthesis and hit enter, and there's the numerical value that we would get from that. Now let's suppose we were using a proprietary software that might be included with a Pearson account, my StatLab, my MathLab. So if I bring up StatCrunch, let me get this in your window. All right, there we go. I think you can see this a little bit better. So what I'm going to do is hit the Stat key. I'm going to choose Calculator, and I'm going to choose Binomial. And it's got built-in Binomial Calculator here. I'm going to type in the values that we have. So in this case, we had 3 trials. Probability of success was 1/4. And then I'm looking for exactly. So I'm going to choose equal. I'm looking for exactly 2 successes. And when I click compute, there's that same decimal value that we got. Okay, so I want to look at a couple other examples here, and what I want to do is let's plug into the formula. Let's write the formula. Let's talk conceptually, and then I'm going to use technology to be a little bit more efficient here. Right? So on this first problem, again, to save a little bit of time, I typed this out. So feel free to pause this video and write this down in your notes if you're taking notes with what we're doing here. So this first question says, what's the probability that an individual is the probability that an individual is left-handed is 0.12, and a class of 39 students use the binomial distribution to find the probability of finding exactly 5 left-handers. Now you might ask a question, how do we know the probability that an individual is left-handed is 0.12? Great question. So like we talked about in our prior probability video, we have classical or theoretical probability, and we have empirical probability. Now there's no way for us in a classical or theoretical manner to, write out all outcomes in the sample space, right? In essence, like rolling a die, I got 6 sides, right? 1, 2, 3, 4, 5, 6. For a left-handed person, this would be like, I would have to collect data. This would be empirical. So I would try to survey, right, or look at all the people in the population and find out how many are left-handed. All right, anyway, I digress there. So when I read this problem, this is binomial because you're either left-handed or you're not left-handed, right? So a success would be choosing a left-handed person, right? Because we're finding exactly 5 left-handed people here. So success is a left-hander, failure is not left-handed, right? i.e. right-handed. So in this case, how many trials do I have? Well, I'm looking at 39 students in the classroom. I'm looking for exactly 5 left-handers. The probability of that successful left-hander is 0.12, and then the failures, 1 minus 0.12, right? So 0.88. Now if we're plugging into our formula, again, remember the probability of 5 of, let me just write the formula, of x successes is going to be the trials choosing x successes, the p-value to the number of successes, the q-value to how many failures we would have. So in this particular example, we have 39 trials. We're choosing 5 successes. Our probability of success is 0.12, and we want 5 of those. Our probability of failure is 0.88, and we're going to have 39 minus 5, or 34 failures. 39 minus 5. Right? So again, I would need to crunch this formula, this binomial coefficient, and that can get really tedious. So let's discuss how we would use our different pieces of technology to do this. All right, so again in Excel, I'm going to bring up Excel. I'm going to click any cell, come up and click on my formula bar. I'm going to type equals. I'm going to start to type binomial. I'm going to choose binomial distribution. Again, it wants the number of successes. So in this case, we want 5 left-handers. How many trials were there? We had n equals 39. What was the probability of a success? We had 0.12. And then is this cumulative? And the answer is no, because we're looking for just exactly 5. So I'm going to hit enter, and it's going to tell me 0.1856 if we round to 4 decimal places. Now, if I'm using a TI calculator, we're going to do what we just did a moment ago. I'm going to go to distribution. So I'm going to do second vars and pull up the distribution. I'm going to scroll down to the binomial distribution. Now, again, I'm not doing a cumulative probability. We'll look at one of those in a second. I'm doing just a single exact probability. So I choose that option. Wants to know the number of trials, wants to know the probability of any particular trial. How many successes did I want? And then let's paste. Then I got to hit enter one more time, and it's giving me that same probability that we just had prior. Now again, if I'm using a proprietary piece of software like my stat lab, I'm going to go to stat calculator binomial, and I'm going to type in all the information that we just did in those prior two. So n is 39, my probability of success was 0.12, and then I want exactly equal to 5, and there's that same value, 0.1856 if we round to 4 decimal places, 0.1856. All right, let's look at a problem where we would have a cumulative probability. Okay, so in this example, let's look at the same question, but this time what we're asking is find the probability of getting at most 5 left-handers. So if we think about this for a second in terms of arithmetic, right? If I have at most 5, I can't have more than 5. So at most means, 5 or less. So in this case, our successes is less than or equal to 5. We're talking about a cumulative probability, right? So what is less than or equal to 5? Well, we could have 0 of them be left-handers, 1 of them be left-handers, 2 of them be left-handers, 3, 4, or 5. So we have a accumulation of a bunch of probabilities. We have 6 probabilities we would have to calculate. We have to find the probability of 0 successes, and then find the probability of 1, and then find the probability of 2, and add all of those together. So again, conceptually speaking, we're finding the probability of at most 5. So what we're technically doing is accumulating. We're looking at a cumulative probability of each of these numbers of successes. Am I going to run out of digital paper? Oh, yes, I squeezed it in. All right. Now, for each of these, I would have to use the probability distribution, right? The formula that we wrote prior. So I'd have to do, 30. So for this one, right, I would have to do 39 trials, choose 0 successes. Oops, sorry. Times. And then I would have the probability of success to the power of how many successes I want, and then I would have the probability of failure times the number of failures. And I have to crunch that number, and I have to do that over and over and over again. What just happened to my digital paper? Now, I don't want to have to go through that painstaking process. Right? If aliens landed on planet Earth and took away all of our technology and said, I challenge you to a statistics duel, then absolutely we could do this by hand. It would be very tedious. So let's, in our conversation, there's the conceptual idea of what we're doing. Let's use the technology that would help us calculate this. All right, now in a TI calculator, again, I'm going to bring up my calculator. I'm going to do second vars, take me to the distribution, and I'm going to hit the up arrow. I think I can get there quicker. So here's the cumulative distribution function. So when I hit enter, right, it wants the number of trials. We had 39. Wants the number, the probability of success. We had 0.12. And it wants the x value. So here's what the TI always does. It's always up to and including the number. So in this case, we're going up to and including 5. So it is always going to include the x value that we type in. So when I type 5, it's saying less than or equal to 5. And when I hit enter and I paste and then I hit enter one more time, there is that cumulative probability. So again, if I went through the painstaking process of finding all of these 6 individual probabilities and adding them together, this is what I would get from that result. All right, now Excel works exactly the same way. So what I'm going to do in this case is click in the cell, click in the formula bar, hit equals, start to type binomial. I'm going to choose the bottom option. Number of trials was 39, comma, that was number of successes, 5 or less, right? And then comma, the number of trials was 39. The probability of any trial was 0.12. And then, is this cumulative? That's the last question. Since this is cumulative, we're going to type true there. And when I hit enter, there's a same value that we got from our TI calculator. All right, and then if I'm using a proprietary piece of software like StatCrunch, the only difference here is I'm going to choose less than or equal to. Right? So I'm going to choose whatever inequality symbol is embedded into my cumulative problem. So I'm going to say less than or equal to, click compute, and we can see that same value there. All right, let's take a look at a slightly different example. I'm picking different numbers here just so we can get some variation. So this problem says, assume that male and female births are equally likely with a probability of 0.5. Right, so 50% chance for a boy, 50% chance for a girl. Let's find the probability of at least 4 boys in 10 births. So again, this is binomial because I have success or failure. And in this case, we're considering getting a boy's success. But of course, girls are much better. So anyway, so 4 boys out of 10 births, and I want at least 4 of them, right? So if I keep in mind my x value is at least 4, so I have 4 or more. I can't have less. So this is x is greater than or equal to 4. Now we have 10 total babies that we're having. The probability of any one particular baby is 0.5. Obviously, Q would be 1 minus 0.5, which would be 0.5 as well. Now, when we think, again, cumulatively, the probability of at least 4, right? That's the probability of 4 and the probability of 5, the probability of 6, and so on and so forth, up to a probability of 10. And again, if we're doing this by hand, this is really tedious and time consuming because I have to calculate each of those probabilities individually. So let's use technology to do this for us. All right, now remember, with the TI calculator and Excel, the way that works is it always goes from 0 up to the number. So when we look at that prior problem we just did, we were finding, at most 5 successes. So it starts at 0 and goes up to 5. And there's no way to change the programming in Excel or TI. It is always going to start from 0 and go up to 5. So something to keep in mind here, we're going to use the complement rule. So the probability that x is greater than or equal to 4, we're going to write as 1 minus a probability that, we're not greater than or equal to 4. Kind of silly to write it that way. So we're going to say the probability that we're less than or equal to 3. Right, so in other words, what I don't want, right? What I do want is from 4 to 10. What I don't want is from 0 to 3. So I don't want less than or equal to 3. So when I use my technology like the TI or Excel, this is going to be the x value that we put in, right? Because it wants to go from 0 up to whatever the x value is. So if I bring up my TI real quick, let me clear. Again, I'm going to go second vars. And you know what, hang on a second. Here's what I want to do. I'm going to do 1 minus the number that we're about to calculate. So I'm going to do 1 minus. Now I'm going to do second vars, go to the distribution. I'm going to go up to binomial CDF. I'm going to type in all the information we had. So the number of trials was we were having 10 babies. The p-value is 0.5 for a boy. And we wanted, and I'm forgetting what we wanted. We wanted to subtract up to 3. So I'm going to subtract up to 3. So subtract up to 3. Let's paste it. Let's hit enter. And there would be our probability of 4 or more. Now if we do Excel, it's going to be the exact same process. Right? I'm going to click a cell, go into the formula bar, type binomial, choose the bottom option. The number of successes, we said, excuse me, and I'm getting ahead of myself. Let me come back up here. I'm going to do 1 minus this binomial probability. The number of successes was up to 3. Again, what we don't want is up to 3. Okay, so the successes was up to 3 that I'm taking out. I had 10 trials, probability of any one success, and is this cumulative? Yes, I need to type true. Yes, it is, and when I hit enter, there's that same probability we got from the TI. Now, if I look at a proprietary piece of software like StatCrunch, and in this case we had n was 10, the probability of a boy was 0.5, and here's the really cool thing here, right? We wanted 4 or more, so I can choose greater than or equal to 4, and when I click compute, there's that same probability that we got. So 0.8281 if we round to 4 decimal places. So 0.8281. All right, so if we're doing a greater than or equal to, the TI and Excel require us to use the complement rule because both of those are programmed to go from 0 up to a number. So we just have to make sure we use a complement rule in those scenarios. Okay, so that's everything I want to talk to you about in regards to binomial distributions. I will see you in the next video.